Yeah.
Recording. Okay, welcome to this free seminar. We are very happy to have Aaron Kettner a second time, and he's going to tell us about Groupoids, Cartan, subalgebras, and Renault's reconstruction theorem. Yes.
Thank you. It's a long title, which is unfortunate. It's like 90% of the talk turned out to be about Groupoids, maybe 10% about the rest. Okay, so what I want to talk about is, so what are Groupoids, first of all? What are Groupoids? How do you take a Groupoid and construct a C-star algebra? Using a construction called the reduced Groupoid C-star algebra. And then in the end, briefly, how do you go back? So how do you take a Groupoid C-star algebra and reconstruct the Groupoid? Okay, so what is a Groupoid? Groupoid is first of all just a set G together with a bunch of structure. Okay, so first of all you have a space of units, the subset G naught G called the unit space. Okay, so this is really just imagine just a set. Okay, some set, and now elements of the groupoid will be arrows between points in the unit space. Okay, so an element of our groupoid, let's say beta, will be an arrow from one point of the unit space to some other point. That's the idea. Okay, so we could have an arrow here and an arrow here. So this is gamma, and then maybe an arrow which starts at some point and then goes to this point where beta starts. And if two arrows are like behind each other in that way, like the range of the first arrow is the source of the second, then we can compose them. And we get a new arrow from first point to the last point, which is the product. So to make that precise, we have a subset E2 of the Cartesian product of G with itself. These are called composable pairs. Okay, so those are like, intuitively, those are the arrows which are like this. The first arrow, the range of the first arrow is equal to the source of the second. And then you have a multiplication, so you have a way of concatenating. So those are the pairs into G, where a composable pair gets mapped to this product alpha beta. So that's exactly what we did here, right? You have two of these arrows, you can concatenate them, and then you have an inverse. So which we just write, or you usually write inverses. So for every arrow, there's like an arrow in the opposite direction. Okay. Now this looks a little, I don't know, for me it looked a bit hard to parse when I saw this for the first time, like it's kind of a lot of stuff. It's like a group, so it's called a groupoid, right? So it should be similar to a group. So it's like a group where you have a lot of units. You don't just have one unit element, you have a lot of them, a whole unit space. And then you cannot multiply any two elements in your group, in your groupoid. You can only multiply those which are composable.
Do you ask that an element is always composable with its inverse, or?
Yes, you do. This is so. Yeah. Oh, sorry. I mean, you need some conditions on all of these methods, right? So that's some conditions. Like you want the multiplication to be associative, for example, right? And you want the inverses to actually be inverses. I mean, right now this is just some map. You want this to have properties which make it an inverse. So like gamma is always composable with gamma inverse, and if you compose them, you get some kind of identity in the sense that gamma inverse eta is always equal to eta for any other eta.
Any other eta where you can make that composition.
Yeah, exactly. Any other eta which is composable. Yeah.
So I don't quite understand it. So I mean, I think of this as a category of repimorphisms, isomorphism, but in this picture, okay, I see that the G0 is the object in your category.
Yeah, exactly.
The G2, these are the morphisms, and then composition, etc. But you have G0 contained in G. What else is inside in G? Is it
It's the arrows. Like G is. I mean, this is.
So then G is like the union of.
No, so sorry. So the
G2 is pairs. G2 is pairs.
The morphisms, but it's composable. No, so it's.
Okay, so
Two morphisms which are composable.
so like G is.
G is G1.
Yeah, G is like the collection of all morphisms, and then you identify. So this is a little. I swept something under the rug here. So you would.
Yeah. Okay, I see.
Identify a point in the unit space with its identity.
Its
identity.
Okay, I got it.
Okay, so yeah. Okay. So yeah, in this, so another definition of a groupoid, if you don't like this, is it's a small category where every morphism is invertible. So it's a category where like everything is just set. You don't need to talk about proper classes, and every morphism is invertible. So the unit space are the objects of the category, and then you have arrows between them, which are the morphisms, right? And you can compose two morphisms if and only if the target of the first morphism equals the domain of the second one. Yeah, considering the amount of algebras here, I should have probably mentioned that.
That's the trick, was missing. So you're identifying the objects with the identity.
Yeah, exactly. Yeah, thank you. Yeah, that's also the way that this is. Like if you compose it with its inverse, you get the identity arrow of that font. Yes. Yeah, great. Yeah, any questions about this definition? I don't have chocolate this time to forward people, but still feel encouraged to ask questions. Now let's talk about some examples. So, all right, one more thing. So, we know what a groupoid is, but it's an algebraic thing. We want to have some topology. So, a topological groupoid is, well, a groupoid with a topology such that all the structure is compatible with that topology. So, G is a topological space, and I mean you can do non-Hausdorff. I always assume Hausdorff, and probably also
You don't like that. I thought you like it.
just for the
That one you don't.
locally compact. I mean, just for the construction of the groupoid sister algebra in a moment. Space. But yes, of course, you can do it as general as you want, and yeah, and all the structure, like all the things are continuous and so on, right? Someone can read my handwriting, also please tell me. Right, so that's a topological. It's like a topological group, right? Like all these things are like what you do for groups, and then you have more units. Examples. First of all, if G is a group, well, homological group. Okay, so then I've mentioned this a bunch of times, but let's write it down explicitly. The unit space is just the single thing which has the identity element of the group. And the composed of the pairs are all the pairs because you can multiply everything. And I forgot something. I wanted to introduce the range and source map. Sorry. Let it go. I forgot. Okay, so I've been talking about arrows and like their domain and range and source and so on. We want to make that explicit, so I'm just going to define the range and the source map. R and S, which both go from the Groupoid to its unit space. And intuitively, the range, like R, if you feed it an element and it spits you out the point in the unit space, which is the target of the arrow, and the source is the same thing. So explicitly, we have that R is equal to gamma. Yes, and S is equal to gamma equals gamma. So, well, I mean, to get the range, you would like to get the range of an arrow, you like, I guess first you take the inverse and then you go back and then you're at the range, and to get the source, you first take the arrow set and then you take the inverse.
So your composition rates back to left?
Yes,
Yeah.
that's
So I guess this arrow in your picture, this alpha beta up there should be a theta alpha instead, because the alpha is
yeah,
one.
that's the next point. Yeah, this keeps confusing me. So you need to read composition of arrows from right to left. You start.
Of course, the category theory for the property is to eventually get that right.
Doing my first round of those this semester, it's been a struggle.
Yeah, right, but it's like composition of work, right? So yeah, that makes sense.
Maybe alpha a subscript is a bit of a superscript. So you don't have to see that.
No.
Yeah, and in the group example, of course, the range and the source are both trivial because there's only one point of the second example, the first example I'm talking about that's not the group, is a topological space. Let's say X. And this is also a groupoid because so the groupoid is equal to X. The unit space is all of X. So like this is a groupoid where you only have unit space. Okay, there's no non-trivial arrows. Then the space is equal to the pairs. Right, nothing is really composable except the elements of themselves. And the range and the source are both equal to the identity. So in pictures, a group is like a point with a lot of arrows on top of it, right? If you want to stick to the arrow picture, unit space is the point, and then you have a lot of arrows over the point. The space is the opposite. So you have your space, and then over each point you have the identity arrow, and that's it. Okay, and so I guess one should think of groups and spaces as being like on opposite ends of a spectrum of groupoids. So like if you want to prove something for groupoids, you would check whether it holds for groups and for spaces. And if it holds for both, then there's a fair chance that it'll hold in general. Yeah. So, any remarks, questions? Yeah, so I don't have that example actually, because I'm not sure how familiar people are with dynamical systems, but yeah, that's right. So my third example is something in between both. So you take the Cartesian product of the space with the group. It's called the group bundle. Here the unit space is the space, and the controls of the pairs are x, g, x, h. So it's important that so to say, the base point in the space is the same. The rest doesn't matter.
So this G that's the group and the G that you the unit space on Earth.
Oh, yeah. Oh, sorry. So I've been writing Groupoids with the Ferry G and the group with the non-Ferry G.
Yeah.
And then this is the thing.
So your curve is only at the top.
Exactly. My
okay.
curve is only at the top. I always write a G like this with
Okay,
a curve at
yeah.
the bottom. So,
Okay.
so I hope that's not too. Some people are confused.
No, I'm back.
Okay.
So really, I always guess because I think about this as a category, I assume the topology was on the category, the objects of the category. The topology is on the morphism as well.
Yeah.
Ah.
Yes. So I should have. I mean, if we want to talk about topological Groupoids, I should have said that we take a topological group.
Well, then we need the new Groupoid that requires those thinkers in minutes. Yeah.
Okay, so in that picture, in that example, the picture would be that you have your space X, and then over each point you have a group sitting. So you have a lot of arrows over each point, but there's no arrows going between different points. Yeah, sorry, the range construction. They are equal again. So you just, you take something and you map it down into the base point. It's like a bundle. It is a trivial bundle if you know what a principal bundle is. Yeah. Example. Then I only have 10 minutes left, which is a bit scary. Okay, so let's maybe skip the first example because I stopped. I still want to do it. So, two definitions, which I'm sure will be important in this talk. So, G is called etal with both R and S are local homomorphisms. Here, local homomorphism is, well, it's locally a homomorphism, so each point is a neighborhood that's like restricted to that neighborhood. You have so this is some kind of discreteness condition. Yeah, so like if you have a map from the square, like the cube 0, 1 squared down to the unit interval, this is not etal because if you take some point, any neighborhood will be like something 2-dimensional. But then down here you can get 1-dimensional things, so you're never going to do it. But then something like covering. Okay, so between compact cluster spaces, local homomorphisms are the things coverings. Covering maps. You take one here. Then homomorphism. So it's some kind of discreteness condition.
Will R&S be continuous?
Oh yes, sorry, yeah. So for that's I guess I swept that under the rug. So like compatible structures, compatible.
It would follow if you assume that the multiplication map is continuous. Well, because the range is also defined in terms of multiplication.
The inverse should be continuous.
And there's all these different equivalents, but basically in the end, all the maps you have will be open and continuous.
But then it's a discreteness condition that topological group is etal. Secondly, the the groupoid is called principal. Yeah. Basically, there are no two different arrows between the same points. So if the ranges agree and the sources agree, then the arrows must agree. Principal. Questions? Because now I will go to the Groupoid sister after, and I will probably erase all that stuff.
Maybe a very quick question. So would example number 4 would have been one where range is different from source?
Oh yeah, that's a good point. Yeah, the fourth example was supposed to be an equivalence relation. So if you have an equivalence relation in a space, you can regard that as a groupoid. But like an arrow between 2 points, you have an arrow between 2 points, you can only use the points are equivalent. And then you compose them by like x comma y, y comma z is equal to x comma z. If you, yeah.
In this case.
And in that case, yeah. So the range would be like the first so equivalence relation. If you have x and y, where x and y are equivalent, then the range would be this guy. So it would be this guy. Body.
The space, if the original space is Hausdorff, it will be.
It's a subset of x
Okay,
times x, right? Yeah.
Yeah.
So everything for me is Hausdorff. It doesn't have to be if you don't want it. Okay. Anything else? Okay, let me in the last, 5 to maybe 10 minutes, like we're a little bit over time, briefly talk about the reduced Groupoid sister algebra and then this Cartan stuff. So if you take an entire groupoid, you can consider compactly defined. Okay, it should be like, in that case, it should be Hausdorff and locally compact.
It's looking at them from my point of view.
It's sometimes locally reversed, but not on
From there,
It's a good thing to know.
Yeah, that looks fine from my point of view.
yeah, it's just from speaker.
So it should, again, tacitly assuming this is Hausdorff and locally compact. Yeah. But most importantly, it's you take compactly supported functions on your groupoid, and that's a star algebra with the following scary looking multiplication. So it's some kind of convolution. Yeah, I guess there's no need to really absorb this now, but maybe you can see that it's some sort of convolution if you've seen a convolution before. well, okay, this, I mean, we need the range of beta to be equal to the range of gamma, so that these guys are composable, because the source of beta inverse is the range of beta, so like let's make sure these two fit together. Yeah, and this is actually a finite sum because we have an entire groupoid. Okay, so this makes sure that like the fibers over points in the unit space are discrete, and then we can do this. And of gamma inverse, and then you take. It's maybe not super clear why it is that way, but it turns out to make sense. And you then complete this into the reduced Groupoid sister algebra. Using left regular representation. So I'm not going to make this more precise. The people who attended my pre-seminar 3 weeks ago will maybe this will ring a bell. Like there we constructed the group von Neumann algebra using some sort of left regular representation. Here it gets a bit more complicated because you have one regular representation for each point in the unit space. So you have like a family of them, and then you need to take the completion and go on. Yeah, that's what happens. So somehow you complete this star algebra into a C star algebra. And this is the Groupoid sister algebra, which I should put right down. So C star reduced to G. And maybe this becomes a little more comfortable with this if I tell you how the special cases, namely, I mean, I told you the main two examples are like groups and spaces, right? So what happens for groups? For a group, this will just be the group C-star algebra. So like the C-star algebraic counterpart to the group von Neumann algebra that we discussed previously. And for spaces, this is just here. And maybe really quickly as a, okay, I will go like 3 minutes over time. Yeah, hopefully not. As a teaser for John's talk, so I mean, the way I wrote it, it's very tempting to wanting to make this some categorical thing, right? Like to wanting to make this meta functor from the category of groupoids to the category of sister algebras. Now the question is, what are the right morphisms for groupoids? The naive guess would be, okay, you just take a map of the underlying sets. So which, yeah.
What is this, the C star norm for the space? If it's not compact, then it should take.
Oh, okay, sorry.
Or is it?
Maybe this.
Okay.
Sorry. Thank you. The naive guess for what a groupoid morphism should be is just a map of the underlying spaces, which is compatible with all the structure. But we see here that this can't work because if you have two groups, a map between a group homomorphism between two groups, then you get a map between the group C-star algebras. But for spaces, it's the other way around, right? So if you have a map from X to Y, you get a map from C naught of, let's say they're compact. Then you have C of Y to C of X. So this is covariance kind of tricky. So it's not going to be, you're not going to be able to naively generalize this to group points. I believe that's what you're talking about.
Yes.
Okay. Then we'll just really quickly write down the definition of Cartan subalgebras. So just or are there questions about this? Questions? So the question is, how can we recognize Groupoids C-star? Or in other words, if I give you a C-star algebra, how can you tell whether there exists a groupoid whose reduced groupoid C-star algebra is isomorphic to the C-star algebra I gave you? And some of the structural property that is important is that of a Cartan subalgebra, which is, I guess, stolen from the word is stolen from the theory of Lie groups. What is this? This is a subalgebra. A. A. First of all, B is maximum abelian. So it's abelian and it's not contained properly in any abelian subalgebra. And then it's regular, meaning that the span of all the normalizers is dense in A, where normalizers are elements in A, which so that n star b n and n b n star are contained in B.
You've got B and N in there.
Sorry?
You've got A and A, such
Yeah.
that N star.
Sorry. And there exists a conditional application. Which is a special kind of map from A to B. That's a concept algebra. Sorry that I'm so brief, but I really want to finish already over time. And then there's a theorem by Renault, which I'm not going to write down now, saying that basically, if you have a Cartan subalgebra in a C-star algebra, you're able to construct a groupoid. Which is a lie because it's just a groupoid, like there's some additional thing you need.
Also, it's only perfected.
Oh yeah.
Yeah.
What does subalgebra mean? Like algebraic, or is it a sub C-star?
Oh yeah, it's a
Sub
C-star
C-star.
algebra. Yeah, good point.
But maximal abelian will imply that it's closed.
Oh, yeah, fair. Okay.
Right. Yeah, so there's this nice reconstruction theorem going back from C-star algebras to groupoids using the notion.
Thank you. Are there more questions?
Would it go the other way then? You have a group with C-star, does it have a character?
Yeah, that's part of the theorem which I intended to write down but didn't. So, like the Cartan in the groupoid C-star algebra will exactly be the functions on its unit space. So this you can regard this as a C-star subalgebra of the groupoid C-star algebra, and it's abelian, right? And it turns out.
There is a condition you have to put on the groupoid though for this to be a.
Oh yeah, thank you. So that's why I defined principle earlier. It's gone now, but that's why I defined principality for groupoids. If you remember that there's like no two different arrows between the same 2 points, and that's what you. That's not exactly.
It's sufficient.
It's a sufficient.
Yeah. And then what happens to the graph C-star? Do they satisfy this condition and they'll always get back?
Generally,
Yeah.
they might have a Cartan, but it's not obvious what it is.
Wait, but can't you build?
They have an NC Cartan.
Can't you always build a groupoid out of a graph? So
Yeah.
Oh yeah, you can do it. Yeah.
I think so.
No,
Wait, but isn't that the original definition of?
it's a groupoid C-star algebra, but it's not necessarily effective.
Yeah.
Because if you build, for instance, if you take the graph with a single loop, but it's on a single point, the C-star algebra you get is the functions on the circle, which is itself a commutative. But the C-star the subalgebra associated to the unit space, I don't think is.
Yeah, in that case, like, you get Z, right? So, like,
Yeah,
it's just
yeah.
an unaffected group, it's
Yeah.
a group.
Are there some questions from the people on Zoom?
Not that I can see.
Let me see. Okay. In this case, that's one last question. Of risk.
So then if you look at G0, that's going to be a subspace that we have the introduced topology. So in fact, you do have a topology on the objects, and the morphisms are going, they're maps that go from the topological space to itself, but they continuous.
Wait, the what?
So if we look, so G0
Huh?
is a subspace of the topological space.
Sure.
Therefore, we have the introduced topology. Now, the morphisms go from objects to objects.
But from a single point to a single point, like there's not really any.
Yeah, okay, good. Okay, super good.
Not entirely.
Okay, here principality is not sufficient. For example, if the political principle.
It's principality is sufficient, but it's not necessary.
Okay, but it's not. Topological freelance.
Yes.
If the action is topological free,
Yeah.
then you have a concept. But I don't know what transformation is sufficient condition, no?
So principality of the transformation groupoid is a free action, a fully free action.
Topological.
Topologically free is enough.
Yes,
Yeah.
but the helmet for the content where we have the sufficient, sufficient condition.
Yes.
Not-
For just general groupoids or
Yes, for group.
effective.
This is the effective is.
Effective is sufficient and necessary.
Oh, okay. So I want to say that. But the effective exactly is topological.
Everyone has a slightly different definition. Right?
So in the second counter setting,
Yeah.
effective and topologically free coincide for Hausdorff groupoids.
Oh,
But as you remove adjectives from your groupoid, you have to be careful about which definition you take. But I'll go over a bit of that in my talk.
Okay, wonderful. Let us thank Aaron.
Sorry, I hijacked you towards the end there, Aaron.
Although Karen did have a comment that I guess it was in relation to this previous discussion about graphs structures. It won't work if there are six, I believe. Or sources if you're in Australia, she said.
Okay. Thanks, Aaron. I feel seen.